Hi, I'm Sanjay Sarma, Professor of Mechanical Engineering at MIT. The video you're about to watch is part of a series produced for SUTD and MIT. Each video will help you learn a pivotal concept in science or engineering. These ideas are the building blocks of your curriculum, and learning them will help you master more difficult material. They will be critical for your work as a professional engineer, a designer, or an architect. This video is part of the problem-solving series. Problem-solving skills in combination with an understanding of the natural and human-made world are critical to the design and optimization of systems and processes.
Hi, my name is Ken Cameron, and I'm a mechanical engineering professor at MIT. Today I want to talk to you about using unit analysis in problem solving. Unit analysis may seem simple, but it's a critical tool for validating your calculations. To understand this example, you should be familiar with the definition of work. In this video, we describe how integration and differentiation affect units. Then we'll do an example problem motivated by physics, computing the work done by a force acting on an object. We use unit analysis to check our work along the way. We use the fact that two numbers can be added or subtracted in an equation when they have the same units. At the end of the computation, we leave it as an exercise for you to check that the answer has the correct units. After watching this video, you should be able to utilize and apply the key properties of unit analysis. When two quantities are multiplied, their units also multiply, and all terms added, subtracted, or equated must have the same units. You should also be able to explain how derivatives and integrals affect units. In December 1998, the Mars Climate Orbiter was launched in hopes of providing detailed information about the atmosphere of Mars. The launch went well. However, a unit conversion error occurred because the two teams that collaborated on the project worked in different units. One used the metric system, and the other the English system. So while the orbiter was intended to fall into orbit around Mars, instead it crash-landed on the surface. So units are pretty important. Before we start the main example, let's discuss how integration and differentiation affect units. The first question is, what are the units of dx? You should think of dx as a very small change in x, or a little bit of x. Recall that a little bit of ice cream is still ice cream, even if it is a very, very small amount. So the units of dx are precisely the units of x, and the d in dx is unitless. So let's do an example. Let's consider the position function x of t with units of meters, where t is time with units of seconds. Then velocity is the time derivative of position, v equals dx dt, and has units of meters per second. Let's look at how the notation is consistent with our physical interpretation. dx has units of meters, and it is being divided by dt, which has units of seconds. So dx over dt should have units of meters over seconds. Now let's look at acceleration, which has units of meters per second squared. We know that acceleration is the time derivative of velocity. So let's go ahead and see how this plays out with the notation. Acceleration has units of meters per second squared, and indeed that is the same unit as you would receive if you were to take a little bit of velocity, which is meters per second, divided by time, which is units of seconds. So indeed this is meters per second squared. So far so good. But when you go ahead and substitute in the fact that velocity is dx dt, we can put it together like this. And let's make sure that this still makes sense. Recall that the differential d is unitless. So anything unitless squared is still unitless. So the numerator here is meters. And the denominator is d, which is unitless. And t squared, time squared, that's seconds squared. So indeed, this expression has the correct units of meters per second squared. We can also determine how integration affects units. Let's use the example of the integral of velocity with respect to time t. We know physically that this is position, which has units of meters. Unit analysis also makes this clear, because v has units of meters per second, and dt has units of seconds. So when we multiply, the seconds cancel, and we end up with units of meters. It might be interesting to point out that the integral symbol doesn't affect units at all. Just like the differential did not have units, it is just a symbol that represents the limit of sums. Since every term in the sum has units of v times units of t, the integral sign, you see, doesn't affect units at all. What we've seen is, given a function f of y, differentiating with respect to y divides the units of f by the units of y. Differentiating twice divides the units of f by the units of y squared. Similarly, integrating with respect to y multiplies the units of f by the units of y. In this example, we'll see how unit analysis can help us check our calculation of the work done by an applied force. In this problem, a machine in a factory is programmed to apply a force to a 3 kilogram object to move it back and forth in the horizontal direction. The position of the object as a function of time is given by the equation x equals 3t minus 4t squared plus 1t cubed, where x is measured in units of meters and t in seconds. Find the work done on the object by the force from t equals 0 to t equals 2. Note that work is done when a force is applied over a distance on an object.
Work.
Let x0 be the position of the object at time t equals 0. Let x2 be the position at time t equals 2. Then the amount of work done on the object is computed by the equation w equals the integral from x0 to x2 of f dx. Let's start by figuring out the units of work. We do this by analyzing our equation, which tells us that the units of work are the units of force times the units of dx. Now, if we forgot what the units of force are, we can use unit analysis again to figure this out. We know that F equals ma, and acceleration is in units of meters per second squared, and mass has units of kilograms. Likewise, the unit of force, also known as the Newton, is equivalently written as kilogram meters per second squared. Recall that the units of dx are the units of x, which are meters. Thus, the unit of work is a Newton meter. So now we know what units our answer needs to be in. So let's start solving our problem. In order to solve our problem, we need to know the force acting on our object. We are given the mass of the object, the position function for the object, and that F equals ma. Because we could determine acceleration as the second derivative of position with respect to time, we can use our given information to determine the force. So let's go ahead and solve this problem, perhaps incorrectly. See if you can catch my mistake. All right, so here we have the position as a function of time, so let's go ahead and differentiate to get the velocity. And we'll go ahead and differentiate the velocity to get the acceleration. All right, and finally, to get the force, we go ahead with F equals ma. So there's my m, and my a, according to this expression, is minus 8 plus 6t. So I look at this and I think to myself, uh-oh, this can't be right, because this doesn't have units of force. This is not in units of newtons, this is in units of kilograms. So this entices me to go back into the problem and try to figure out what went wrong. Looking back up at the first equation, the position, I see immediately that something has gone wrong, because position is in units of meters, and each of these terms is definitely not in units of meters, and in fact, they don't even agree with each other. That tells me that there had to have been units for each of these constants that somehow got swept under the rug. So let's be rigorous and put those units back in. The unit in front of here would have to be something of units of meters per second. That's the only way that I can multiply by a time and back out meters. Okay? So all along there had to have been meters per second in there, and we see that this actually gives us something physical, because 3 meters per second is in fact the initial velocity. Okay? Let's go back into this term here and see that I have a t squared, and I need something with units of meters per second squared if I'm going to ultimately get from this term something that has units of meters. And lastly, we have this term over here, which has a t cubed. And likewise, the missing unit must have units of meters per second cubed, which physically is the unit of jerk, or the rate of change of acceleration. You may want to pause the video here and find the units for the constants in the formulas for velocity and acceleration. Show that these units agree with the units you find by differentiating x of t. So now that you've checked the units of acceleration, let's go ahead and put it back into the force formula and see that everything works out OK. So we got F equals ma. M, as before, is still 3 kilograms. And the acceleration written with correct units is minus 8.0 meter per second squared plus 6.0 meters per second cubed times time. And to see that this whole thing has units of newtons in the end, let's go ahead and expand it and see that each term, in fact, has units of newtons. We get minus 24 kilogram meter per second squared. That's a newton, so that's good. Plus 18t kilogram meter per second cubed. And just to check this, we note that while this does not have units of newtons, time is measured in units of seconds. So if you insert some value for time in units of seconds, like we said in the problem, in fact, the seconds will cancel here, and you'll get a second squared on the denominator. And indeed, this term is entirely in units of newtons as well. So now that we have verified that the force is indeed in units of newtons, let's go ahead and compute the work integral.
Work.
Recall what that is. That is the integral from x0 to x2 of f dx. OK? Well, we've got the force, so let's go ahead and put that in. I'm going to not put the units in for now. We'll have an exercise later that you will do that. What do we get? x0 to x2 minus 24 plus 18t dx. So we look at this and we realize that we actually have a slight problem because the force, as you can see here, is written in terms of time, and yet we're integrating over x. But this really is pretty easily resolved. Just remember that a small change in x dx is equivalently the velocity times a small change in time. In case you forget, it's pretty easy to see when you express the velocity as dx dt, because then you multiply it by dt. And in fact, you can even see that in the end, you get something that is a small change in x. So in your calculus class, sometimes this little maneuver is called the change of variable. So let's go ahead and do that. This means our integral can be written as an integral over time from time equals 0 to time equals 2 of force times velocity times dt. We write f as ma. And we recall that acceleration is the time derivative of velocity. So now we see how to integrate this. And we find that the integral is m times velocity squared divided by 2, evaluated at the 2-time endpoints. Plugging in our formula for the velocity and evaluating, we get that the answer is negative 12. I intentionally left off the units while doing this computation. Now I leave it as an exercise for you to use unit analysis to check that this integral does in fact give you Newton meters or joules, the units of work. In the example, we saw that when you are adding numbers with units, it is important for those numbers to all have the same units if you want your quantity to have any physical meaning. We also learned that the differential quantity dx has the same units as x. We also saw that it is helpful to use unit analysis to check your work along the way. You can see now that unit analysis can be a useful part of your problem-solving strategy. It is important to understand the properties of units and how they are affected by mathematical operations. Checking units at the end of a computation is useful to see if the solution is reasonable. Sometimes, unit analysis can suggest a formula for an unknown quantity in terms of given information. But physical knowledge is necessary to validate the solution completely.